Your phone just connected to a cell tower it has never seen before. In under a second, it agreed on secrets strong enough to encrypt your calls, hide your identity, and spot anyone tampering with control messages. How? The answer is not one magic password. It is a key hierarchy, a carefully layered chain of derived keys defined in the 5G security standard TS 33.501. Think of it like a building with locked floors. The master key never leaves the vault. Each floor gets its own key, cut from the one above, so a breach on the ground floor cannot open the penthouse. In 5G, that chain delivers three jobs at once: authentication, proving who you are; confidentiality, hiding the bits; and integrity, detecting tampering. Over the next minutes, we will walk the exact path on the hierarchy diagram, from the root key K through CAUSFF, KCAF, and CAMUF out to the radio keys that protect real traffic, with concrete examples of onboarding, streaming, and mobility. Every story in this diagram starts with one long-term secret called K. K lives in exactly two places. On your side, it sits inside the USIM, the secure chip on your SIM card. On the network side, it sits in the home operator's authentication credential repository and processing function, the ARPF, inside the Unified Data Management Node, or UDM. K is provisioned when the SIM is made. It is never sent over the radio. When you attach, the home network runs 5G AKA, authentication and key agreement. From K, it derives two intermediate keys, CK, the cipher key, and IK, the integrity key. The USIM computes the same CK and IK from the same challenge. Those two values are the raw material for everything above them in the hierarchy. Here is the part that matters. An attacker sniffing the air interface never sees K, and never sees CK or IK in the clear either. They only see challenges and responses that prove both sides share K, without revealing it. That is the foundation the rest of the tower is built on. Zoom into the home public land mobile network, the HPLMN, on the network side of the diagram. After 5G AKA produces CK and IK, a key derivation function folds them into a new key, CAUSF. CAUSF is the authentication server key. It is held by the AUSF, the authentication server function, which is still in the home network domain. Why invent another key instead of just using CK and IK everywhere? Separation of privilege. CK and IK are AKA outputs. CAUSF is a stable anchor that represents this subscriber just authenticated successfully for the rest of the 5G core. Serving networks will need a key, but they should not inherit the home network's deepest secrets. So the home network keeps K and the AKA machinery. The AUSF keeps CAUSF, and from CAUSF, the next hop will create a key aimed specifically at the serving network. If you remember only one thing from this scene, CAUSF is where home authentication becomes a reusable security anchor, without exposing the root. Now cross the boundary into the serving network, the network you are actually camping on right now, which might be your home operator or a roaming partner. From CAUSF, the system derives KSEAF, the key for the SEAFE, the security anchor function. The SEAFE is the serving network's front door for security. Binding a key here means the serving side can prove it participated in a fresh authentication without ever learning K. From KSEAFE, the access and mobility management function, the AMF, derives KAMFE. KAMFE is the workhorse for the serving core. It will parent the NAS protection keys and the keys that go toward the radio access network. Why two steps, KAMFECN then KAMF? Because security anchor and mobility manager are different jobs. You might keep the same SEAAFENAFE stethoscope while the AMF changes during mobility. Or you might rederive KAMF horizontally when policy says the old AMF should not keep decrypting your NAS. The hierarchy makes those moves possible without calling the home network every time you change cells. That is deliberate engineering, not accident. Look at the other half of the diagram, the UE side. Security only works if the phone can compute the same keys the network just derived. The work is split. The USIM holds K and runs the AKA algorithms that produce CK and IK. Those secrets do not spill into the app's processor. The mobile equipment, the ME, meaning the phone's modem and secure key derivation code, then runs the same key derivation functions the network runs. It builds CAUSEF, then KSEF, then ChemF locally. There is a parallel path on the diagram for non-3GPP access, EAP aka prime. That path produces CK prime and IK prime. Then a CAUSEF that plays the same anchoring role when you join the 5G core through a Wi-Fi door instead of a cell tower. The symmetry is the point. No key is downloaded from the network like a file. Both ends start from shared secrets and walk the same KDF steps, so they meet in the middle with identical CAMF, ready to protect NAS and to unlock the radio keys. CAMF still lives in the AMF, the base station. The gNB must not receive CAMF. If it did, a single compromised tower could impersonate the core. So the AMF derives a dedicated access key, kGNB, and alongside it the next hop key material, often written NH on the diagram. kGNB is what the serving GNB actually uses as the parent for radio interface keys. NH is the forward security fuel for handovers. We will use that in the mobility example. There is a sibling path through the N3IWF, the non-3GPP inner working function. When you attach over untrusted Wi-Fi, the N3IWF plays a role analogous to the gNB at the edge of the core, and it receives its own derived key from the same family of decisions. Same hierarchy idea, different access door. Horizontal separation is the design win. Compromise a gNB and you may threaten that cell's radio keys. You do not automatically climb into CAMF, KSEF, KAUSF, or K. Each arrow on the diagram is also a firewall. At the bottom of the hierarchy, the keys finally touch packets. 6 names show up again and again in TS 33.501, and they pair into 3 planes. From conf, you get the NAS pair, knas-int for integrity and knas-enc for encryption. These protect mobility and session-management signaling between the UE and the AMF, registration updates, PDU session setup, and similar control. From kGNB, you get the RRC pair, krrc-int and krrc-enc. They protect the radio resource control channel, handovers, measurements, reconfigurations, the nervous system of the air interface. And you get the user plane pair, KU-enc for encrypting your actual PDCP data PDUs, and optionally KU-int when user plane integrity is enabled. That last one is easy to overlook. Encryption hides content, integrity stops an attacker from flipping bits in your traffic without detection. If you map one mental model, NAS is UE to core control, RRC is UE to gNB control, user plane is your apps. Different locks, different parents, same hierarchy. Put the whole diagram in one frame. Left column, home PLMN, UDM and ARPF hold K. 5G aka yields CK and IK. AUSF holds KOSF. Home never ships K to anyone else. Middle column, serving network. KSEAF at the SEA fee, KMF at the AMF. Then KGNB and NH toward the radio. NAS keys branch from KMF. The serving side is powerful for mobility, and still cryptographically beneath the home anchor. Right column, UE. USIM holds K. ME derives the chain in lockstep, KOSF, KSEAF, KMF, then RRC and user plane keys for the active gNB. Read top to bottom and you see derivation. Read left to right and you see trust domains. That two-axis layout is why the picture looks busy at first glance. It is not clutter. It is a map of who is allowed to know what. Once you see those two axes, the rest of 5G security procedures are mostly which arrow do we walk next. Example 1. A brand new IoT sensor onboarding onto 5G for the first time. Step 1. Power on. The device does not shout its raw permanent identity. It sends a concealed identifier, the SUCI, so passive listeners cannot harvest permanent subscriber identities off the air. Step 2. The serving network asks the home UDM and ARPF for help. Home builds an authentication vector from K, challenges, expected responses, and the key material that will become CK, IK, and then CAUSF. Step 3. The challenge hits the USIM. The SIM verifies the network's MAC, proves it knows K by returning the response, and emits CK and IK inside the secure boundary. Step 4. Both sides derive CAUSF, then KCAF for the serving SES, then KSAMF for the AMF. The sensor and the network now share a serving core key without ever transmitting K. Step 5. KSAMF yields KGNB and the leaf keys. The first user plane packets from the sensor leave encrypted. Factory floor, smart meter, camera, same ladder. The hierarchy turns a tiny chip and a distant vault into a live, least privilege session. Example 2. You start a video stream on your phone. Which keys actually touch those packets? Your app hands PDUs to the modem. On the air interface, the PDCP layer encrypts with KU-INC and may integrity protect with KU-INT. Those keys came from KGNB, which came from CAMF, which ultimately traces back to the authentication you did when you registered, not from a per-app password. Meanwhile, the control plane is not idle. RRC messages that retune your radio use KRRC Inc. and KRRC Int. If the stream triggers a QoS or session tweak, NAS messages use KNAS Inc. and KNAS Int between UE and AMF. Notice what does not touch the video PDUs. KSF, KSEF, and KMF stay upstream. The gNB only ever needed KGNB and the leaf keys. So if someone steals a small cell's key store, they do not automatically obtain the home operator's root or even your NAS keys for the whole registration. The diagram's layering is the blast radius control for real traffic. Example 3. Mobility. You are on a high-speed train. Cells fly by every few seconds. You do not retype a password, and you should not rerun full home authentication for every tower. For gNB handover, the hierarchy uses the next hop key, NH, and a chain counter. The target gNB receives a fresh KGNB derived so that the source gNB cannot compute it afterward. That is forward security. Yesterday's tower is cryptographically retired for tomorrow's radio traffic. When mobility crosses AMF boundaries, KMF can be rederived from KCAF or via horizontal derivation rules. So NAS keys refresh. Full AKA back to the home AUSF is reserved for when policy, timers, or trust require a new anchor. Not for every cell edge. Roaming makes the left side of the diagram vivid. Your HPLMN still owns K and CAUSAF. The visited serving network only ever receives derived anchors like KCAF. You keep streaming music across a national border because the hierarchy was built to rekey downward without exposing upward secrets. That is the train scenario the standard quietly optimizes for. One hierarchy, many locks. Remember the chain K to CK and IK, to CAUSF, to KCAF, to CAMF, to KGNB, to the leaf keys that protect NAS, RRC, and user plane. Root K stays in the USIM and the home ARPF, never on the wire. The home network authenticates. The serving network receives only derived anchors. The UE mirrors the chain so both ends share session keys. Leaf keys specialize by plane and by EINTs versus integrity. Mobility rekeys downward without exposing upward secrets. Next time you see the TS33.501 key hierarchy figure, do not scan it as alphabet soup. Read it as a building directory. Who holds which floor, which door each key opens, and why a breach on one floor should not unlock the vault. That mental model is the whole point of the diagram and the backbone of 5G security.